Section 21.3, magnetic force. The two objectives here are to determine the force or strength of a magnetic field and to find the direction of the force on a charge moving through a magnetic field. So what we know from experimentation is that a stationary particle that's charged doesn't really interact with a magnetic field. It doesn't feel any force applied to it, but a moving charged particle does. So the particle feels that force at a maximum when it's moving perpendicular to the field, and that's the case we're going to look at this whole time. At other angles is decreased, and when it's moving parallel to the field lines, it's actually not feeling that at all. So it cannot be moving in the same direction as the field lines in these examples we're looking at. Our formula here is going to be B, which is the magnetic field strength, equals F mag, which is the magnetic field force, over the product of the charge and the velocity of the particle. The units here are going to be Tesla. Tesla named after Nikola Tesla. He was an electrical engineer, a mechanical engineer, he was a physicist, a bunch. He was a Serbian-American that lived in the 1800s. His major contribution was to do with alternating current and electrical supply systems. But here we know that he's named after this because of, again, magnetic fields that are involved in those electrical systems. What we'll see here is that when we solve for the magnetic field, we get BQV equals F magnetic. So this tells us that the magnetic field is directly related to the strength of the magnetic field, the magnetic force is directly related to the strength of a magnetic field. It's also directly related to the charge of the particle, and it's also directly related to the velocity of the particle. So a particle sitting still has no velocity, so no force is felt. When there's no magnetic field produced or present, there's no force felt. If there's no charge in the particle, if it's a neutral particle, there's going to be no force felt. Now what our right-hand rule tells us is the following. If you can orient your fingers in the direction, in your pointer fingers, your main four fingers, in the direction of the magnetic field, and you orient your thumb in the direction of the motion of the particle, the velocity, which way it's moving, your palm points in the direction that the force would be felt on a positive charge. So in this case, if the field was acting up, and let's say this thumb was to the left or something, then this would come out of your palm. So when you do this, you're going to have to practice more with your hand. So if say the field was acting upward, and then the particle was moving to the left, right, there's our hand, this ugly hand here. This means that the force would be into the page. I'm going to put a little X all over the place. This means into the page. So the force felt would be a force into the page. That would be the force. The field would be upward, and the velocity would be left in this case. Why do we call that into the page with X's? Because think about darts. If you were to throw darts, what you would see X's from the tails, the little feathers or the little tails in the end of a dart. If a dart were coming out of the page towards you, you would see like a dot or the tip of the dart coming at you. So if there's dots, it means out of the page. If there's X's, it means into the page. And that's the force in this case. Let's look at an example of this. So in this example, a proton moves straight upward. So right away the velocity is upward, so your thumb is facing up. Next it says, through a magnetic field that points to the east. So I'm going to say that east is to my right in this case. Okay, east is to the right, say west, east. Into the page is north. Right, into the page is north. And south is coming at you, or out of the page. That's what south is in this case. Up is up and down is always down. So your thumb is facing up or away from the ground, and your magnetic field is pointing east. Well, the palm would be into the page in this case, so our answer could be into the page or it could be north. If you're given east, then we'll use north. If we're told to the right instead of east, if it's to the right, then we might say into the page. So we know that the magnetic field strength is 3 Tesla. We know that the velocity of the particle is 2 times 10 to the 8 meters per second. We know that it is a proton, so the charge is 1.6 times 10 to the negative 19 coulombs, or the elementary charge. And we're trying to find the force acting on this object. Again, we know it's going to be northward, the force, or into the page. Either way we could say is fine. To find that force, we solve for F like we did in the last example, or we did when we had the formula. Force equals BQV. It's the same formula we just had when solving for force. Plugging in the magnetic field times the charge times the velocity, we get a value of 9.6 times 10 to the negative 11 newtons. And again, this is north or into the page. What you're going to notice is that there's a very high velocity. Well, that makes sense because the mass of a charged particle is extremely small. It is extremely small. Now, what if this charged particle is moving in a field and the magnetic field is into the page? We can see here B, right? B is the magnetic field, and all these X's are showing that the magnetic field is into the page. So if the field is into the page, take your fingertips and try and point them into the page like that. I'm trying to draw in 3 dimensions. Your thumb is going to act up, which means that if your fingers are into the page and your thumb is up, your palm is going to be facing this way. So put your fingers into the page and your thumb upward. Your palm is going to face inward. That's this magnetic field right here. Okay, so the velocity is up, the particle is moving this way, but the field is pushing it with a force to the left. So if it's being pushed to the left, it's going to want to tail off like this. Well, as it tails off, what happens is your fingertips still act toward the page, but the velocity of your thumb keeps pushing this way, which means that the force is inward. Then the thumb is here, with the fingers into the page again, force is this way. Then the thumb is this way, when your fingers are into the page again, which makes the force this way. So no matter what, if you keep your fingers pointing into the page and your palm toward the center, or your thumb tangent to the motion, or we would create your palm, it would make your palm go toward the center. So the magnetic force here provides a centripetal force, which keeps it in circular motion. So in this case, what we have here is the magnetic force, obviously. And the last part is, again, BQV. But that is equal to the centripetal force, which equals mv squared over r. So we can set these two equations equal, getting, again, BQV equals mv squared over r. The v's on each side cancel, one of them at least, giving BQ equals mv over r. This is a good relationship to know, but you don't have to memorize it because you know this formula and this formula. Just set them equal to each other when an object is in circular motion. Now keep in mind in these equations or in these problems that the magnetic force is providing this centripetal force. Just like when a car is going around a racetrack, the force of friction provides the centripetal force. Or when an object is in circular motion around a planet, the force of gravity provides the centripetal force. So in those cases, we'd have different equations here and set them equal to the same number, though, or the same quantity. So here we have the magnetic force. This could be gravitational force, this could be the frictional force, but no matter what, it equals mv squared over r because it's what's providing the centripetal force in the problem. Example 2 says a proton is moving through a magnetic field with 2.5 Tesla. So the magnetic field strength is 2.5 Tesla. If the velocity of the proton is a very large number, 2.5 times 10 to the 7 meters per second, find the radius of curvature of the path. So let's go back to that formula we had. We had BQV equals mv squared over r, which gave us BQ equals mv over r. Well, you know B is 2.5 Tesla. We know the charge on a proton is 1.6 times 10 to the negative 19 coulombs. We know the velocity and the mass. Mass is 1.7 times 10 to the negative 27 kilograms. And the velocity is 2.5 times 10 to the 7 meters per second. So we're solving for the radius of curvature, so r equals mv over bq. Remember that we're just flipping these two quantities to solve for r. Make sure that bq is in parentheses in your calculator when you calculate it. If we plug in these four numbers, we end up getting a radius of 0.106 meters, or approximately 10.6 centimeters. So this would be the radius of curvature. This is an example that is similar to the particle accelerator, or like the Hadron Collider, something that gets particles moving in circular motion so they could collide and look at smaller particles, and we can investigate science further. This is analogous toward that, or to that. And it's also a lead into the idea of like those high-speed Japanese trains you see that run on magnetic planes or magnetic fields. Or the idea of quantum levitation if you want to search a YouTube video for quantum levitation or look at news form for that.